So how the stability is increased in both the phase lead as well as lag compensators. So in both cases it is going to be the phase margin which is going to be increasing. So how is that going to happen? First we will take the case of phase lead compensator. You have to choose properly so that stability is achieved. There is a chance in which stability can be reduced as well in a phase lead compensator. So how is that happening? So for stability, we will be needing both the magnitude as well as the phase plot, right? So this, let us say this is the magnitude and this is the phase plot. Let us say that for the uncompensated system, that means the phase lead compensator is not included. Then let us say the magnitude plot is something like this. Once you add the phase lead compensator, what will happen? The magnitude is going to increase, then the plot is going to be something like this. At each and every frequency, if you take the with compensation plot is going to be having a higher amount of magnitude. Okay, so you can write here, this is the uncompensated plot and this is the compensated magnitude plot. Okay, so now we can see here, this will be the gain crossover frequency for the uncompensated plot, and here we can write omega g dash for the compensated system. Okay, and the plot, let us say it's something like this for uncompensated system, and for a compensated system, let us say it is here. Now how do you find out the phase at the gain crossover frequency? You just have to drop the point onto this. So this is the phase for uncompensated system. What about for the compensated system? This is going to be like this, right? So we can see that this new phase, that means with compensation, this is going to be of a higher value. So this is the desired case. Phi dash is greater than phi. This is the desired case because phase margin is equal to 180 plus the phase at omega g, gain crossover. Now phi dash is greater than the uncompensated thing, then the phase margin for the compensated case is going to be greater. So the stability is going to improve. Now the plots were slightly different. Okay, so this is the magnitude plot, and we will take the uncompensated system something like this, and the compensated system we can take something like this. Okay, now what will be this omega g dash? You can write here uncompensated system, and this is the compensated system, and remember this is the magnitude Bode plot. Now if you draw the phase Bode plot, the uncompensated phase plot, let us say it is like this, and the compensated phase plot, it is say like this. Okay, so this is compensated and this is uncompensated. Now how will you find out the phase margin? From the gain crossover, you drop onto the phase plot. This will be the phase for uncompensated system. So we will take it as phi. Now for compensated system, it is going to be, if you drop from the compensated magnitude plot, you are going to get here. Okay, so this is phi dash. Now here you can see that phi is greater than phi dash. Now this is the undesired case. That means the stability is reducing. Why? Because the phase margin is equal to 180 degrees plus the phase at gain crossover. So higher is this value, higher will be the phase margin, better will be the stability. But in this case you can see that for the uncompensated system the phase margin is higher because this phi is greater than phi dash. Okay, so in this way, with the depending on the plot, we can ascertain whether the stability can be increased or it can be decreased. Both cases are possible. Similarly, if you take the phase lag case, okay, here also both the cases are possible. So we will start with the magnitude plot. This is the phase plot. Now here what is going to happen? If this is the uncompensated plot, okay, you can write down here, this is the magnitude and this is the phase plot. Then what will happen if there is a compensation? The magnitude will reduce because this is a phase lag compensator. The magnitude Bode plot of phase lag, it was negative, right? So the compensated system is going to be like this, okay? And this is the new gain crossover frequency omega g dash, and this is omega g. Similarly, the phase, if you take, it is going to be uncompensated system. Let us say this is the uncompensated system. Then the compensated system is going to be lesser at any frequency. If you take at any one frequency, the uncompensated system phase is going to be higher than the compensated phase. Now, how do you find out the phase margin? You drop a line onto the phase plot from the gain crossover frequency, right? So this is going to be for compensated case, and similarly for uncompensated case, this is going to be the phase, okay? So you can take this as phi dash and this is phi. So you can see here that this is the desirable case. Why? Because phi dash is greater than phi, okay? Stability is going to be increased. Now, if you take another case, slightly different plots if you take, okay? Let us take this to be the uncompensated plot and this to be the compensated plot. You can write down here compensated and this is the uncompensated, you can write, okay? So now the phase plot, if you draw, this is the magnitude plot and this is the phase plot, okay? So now the uncompensated case, if you draw like this, and the compensated case, you're going to draw a little farther away, okay? So this is the uncompensated case and this is the, compensated and this is the uncompensated case, okay? Now we have the gain frequency of compensated system here. This is the uncompensated system, okay? Now if you find out the phase, this is going to be phi dash, and similarly from here if you draw, this is going to be phi, okay? So you can see here this is the undesirable case. Why? Because phi is greater than phi dash. So this is undesirable because the phase margin will reduce, okay? So this is how, using the phase lead as well as phase lag compensators, it is possible to either improve the stability or worsen the stability. So you just have to be careful of that. That is why trial and error is the method to go whenever there is a design problem at hand.